Hello again, I'm Lavinia Heaton, and we're looking at the average rate of change today. Now let's say we were taking a trip. We're on a highway here, and we're traveling, and we start at mile marker 250, get on the freeway, and we go down to mile marker 370, and we decide we want to check and see what our average rate of speed is. So we think, I started at 9 o'clock, and now it's 11 o'clock, and I have traveled how many miles? We have traveled 120 miles. And what's our time? From 9 in the morning till 11 in the morning would be 2 hours. So 120 divided by 2 would be 60. And you might say, I'm traveling at 60 miles an hour. Does that mean you were traveling at 60 miles an hour the whole trip? Probably not. More than likely you went 70 just as much as you could, and then somebody slowed you down and you might have to slow down to 50 until you could pass that person. And then you might have even stopped for a rest stop in 2 hours. So you'd be going 0 miles an hour then, wouldn't you? So when we say average, we mean it's what we average, not what we're going every minute of the time. Now, calculus will actually help you figure out the instantaneous speed or velocity that you're traveling. But what we do with distance equals rate times time is get an average rate. And remember that if I solve distance equals rate times time for rate, I would divide by t, and I would get our rate or speed equals distance over time. And here's our distance that we traveled. Here's the time we traveled. And that's how we figured the average, wasn't it? Notice we subtracted mile markers and we subtracted times to get the total time traveled. That's basically what we're looking at when we do the average rate of change. For instance, if we want to write an equation for where we are, we could say y equals, I started at mile marker 250, I'm averaging 60 miles an hour for every hour, where x would be the time traveled in hours, and y would be the mile marker we were on, right? Look at the coefficient of x. We call that the slope of a line because this is linear with y to the first and x to the first. So we would say the average rate of change is 60 miles an hour. We also call it the slope of a line. So the slope of the line gives us the average rate of change for that particular line. And that's what we're basically looking at here. So let's say that we have a function f, and we have a point a, f of a, and a point b, f of b. That simply means that one of the x's is going to be a, and the y that goes with it is f of a. Then we have another point, our second x, and then the second y. There are two distinct points on a graph of a function y equals f of x. Then the average rate of change of f from a to b is delta y divided by delta x. And d, delta here, actually stands for the change in y, and then we divide it by the change in x. So let's think. Our x sub 2 and our x sub 1 are b and a. There it is. The change in y sub 2 minus y sub 1. Let's write that down. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That looks like the slope formula for a line, doesn't it? And that's exactly what we're dealing with, the slope formula of a line, when we're finding the average rate of change of a line. So let's see how we might use this. Find the average rate of change of the function f of x equals 4x from x sub 1 equals 0 to x sub 2 equals 3. Now if we remember what we're talking about, that the slope of a line is its average rate of change, we can just immediately say that the average rate of change equals 4. But after we've worked several problems with different equations, it might not be as apparent to us. So let's do it by the delta y divided by delta x, or basically the slope formula, y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Well, to make this go, I not only have to have an x sub 1 and x sub 2, I've got to have a y sub 2 and y sub 1. So I'm going to find points. And my points have the x given, 0 and 1, and 3 in the other. Now we need to find the y that goes with x is 0. If I plug in 0 right here, I get f of x, or y, equals 4 times 0, which is 0. So my point is 0, 0, because I found the y. So that is y sub 1. Y sub 2 goes with x sub 2 being 3, so I'll plug in 3 and get 12 for y sub 2. Now I'm ready to plug in the slope. Y sub 2 is 12 minus y sub 1, which is 0, divided by x sub 2, which is 3, minus x sub 1. So I have 12 divided by 3, which is 4. That's what I expected, because a line gives away what its average rate of change is, because its slope is its average rate of change. So that brings up the question. What happens when we have a curve that's not a line? What if we have a curve, a U-shaped curve? We've looked at some of those already. And we want the average rate of change maybe from this point to this point on the curve. Well, we can't very well use the slope of the parabola per se, can we? But what if we found the slope of the line passing through the 2 points we're interested in? That's what we would use when we don't have a line. We would use the secant line connecting the points we're interested in. So if we want to find the average rate of change of the function f of x equals the square root of x from x sub 1 equals 4 to x sub 2 equals 16, we can do that. It's going to be the slope of the line connecting the 2 points, where the x of the first point is 4 and the x of the second point is 16. So the first thing we want to do is come up with our points. Our first point has 4 for its x, and we'll find its y. The second point has 16 for its x, and we'll find its y. So our y equals square root of 4, which is 2 for this point. And since that was x sub 1, this 2 is our y sub 1. And then here our x is 16, so plugging in our f of x equals square root of x, we get y equals square root of 16, or 4. And 16 was our x sub 2, and 4 is our y sub 2. All right, now that we have our points, we're ready to find the average rate of change. Which is going to be the change in y divided by the change in x, or our familiar slope formula. So we get y sub 2, which is 4, minus y sub 1, which is 2, divided by x sub 2, which is 16, minus x sub 1, which is 4. So I have 2 divided by 12. 2 goes into 2 once, goes into 12 6 times, and we have 1/6 for our average rate of change. So we got the slope of a line that passes through the 2 points rather than actually the slope of a line, since our function was not linear. Now notice that when I reduced 2/12, I made sure I struck that 2. I said 2 goes into 2 once and put a 1 there. And the reason for that is I often see that some people will give me a 6 rather than 1/6. They forget all about that top number being 1 unless they write it down. So make sure you write that down if you need to. And that is average rate of change.